Welcome to Calc 3. This is section 14.1, line integrals examples. So let's let C be the line segment from 0 to 1, excuse me, from the point 0, 1 to the point 1, 1, and then continuing from the point 1, 1 to the point 1, 0. And then surface be f of xy equals x plus y squared. And let's find the area under the curve of the area under the surface on this function f. So as we go about this, let's notice that we can break this up into two different curves. Let's let this section be curve 1, and let's let this line segment be curve 2. We can use this property because as we go along the curves, we can see that one of the properties of line integrals is that we can break up our curve into the two segments. So along curve 1, we can have r be the interval, the vector value function t comma 1, where t goes from 0 to 1. So then r prime is equal to 1 comma 0, and the magnitude of r prime is equal to 1. Along curve 2, r is the vector 1 because our x never changes, 1 minus t, where we're preserving the same time interval. And this is important because to break up our curves, we need to preserve our time intervals. And then by definition of what our curve is. So let's recall our definition here, that if we're breaking up our curve f of s ds, we can do this along these two separate curves. So this is a property of line integrals that we're using. So now along this curve, we have along f, we can break this up, and so we have along 0 to 1, we have the function t plus 1 squared times our magnitude, which is just 1 dt, plus a second interval 0 to 1, 1 plus 1 minus t squared times 1 dt. So this becomes, we can combine these two intervals because we chose our t values nicely, and we can combine this and we get solving this integral, we can get t over 2 squared plus t plus 2t minus t squared plus t cubed over 3, all evaluated from 0 to 1, and this equals 2 plus 2/3, or excuse me, 2 plus 1/2 plus 1/3, which equals 2 plus 5/6, and this is the area underneath that curve. So the next example, let's set up but not solve the line integral for the curve parameterized by this ellipse. 2 cosine t comma sine t on the interval t is an element of 0 to 2 pi. For the surface, 10 minus x squared minus y squared. So setting up this problem, so we have our curve r of t, so we need r prime of t. So this gives us -2 sine of t, comma cosine of t. Our magnitude of this velocity vector is equal to the square root of 4 sine squared of t plus cosine squared of t. Notice that we have a sine squared and a cosine squared, but they don't have the same coefficient, so we can't factor that out. So then our line integral becomes 0 to 2 pi of 10 minus 4 cosine squared t minus 2 sine squared t. Again, we can't factor out the cosine and the sine squared. And this is all times the square root of 4 sine squared t plus cosine squared t dt. So now we've set up the integral and can use appropriate methods to solve this. And then one more example, let's let C be defined by the parameterization r of t equals 3t, 4t on the interval t equals 0 to 1. And we're looking for the area above the xy plane below this curve. So when we're looking at this, when we're looking for the area above the xy plane, we're letting our surface f of xy be equal to 1. That's a key point here. So when we're looking at this, our r prime of t is equal to the vector 3, 4, 1. So that means our magnitude of r prime is equal to the square root of 9 plus 16 plus 1, which is equal to the square root of 26. So our curve goes from 0 to 1. Our f of xy is equal to 1 times the square root of 26. So we get the square root of 26 is the area above the xy plane underneath this curve. So if you have any questions, as always, please feel free to let me know.